Okay, so good day everyone. Our topic for today is about power and effect size. Like statistical significance, statistical power depends upon effect size and sample size. So if the effect size of the intervention is large, it is possible to detect such an effect is a smaller sample number, whereas a smaller effect size would require large sample sizes. So what happened to power when effect size increases? The statistical power of a significant test depends on the sample size. When n increases, the power increases. The significance level when E increases, the power increases. So the effect size, when the effect size increases, the power increases. What is the relationship between effect size and power? So the statistical power of a study depends on the effect size and sample size. As the effect of the intervention decreases, more subjects will be needed to have adequate power. That is, to decide that no difference is true finding. So thus power increases with sample size. Increasing sample size makes the hypothesis test more sensitive, more likely to reject the null hypothesis when it is in fact false. Thus, it increases the power of the test. The effect size is not affected by sample size. So what is influence of effect size? Effect size is quantitative measure of the magnitude of the experimental effect. The larger the effect size, the stronger the relationship between two variables. And you can look at the effect size when comparing any two groups to see how substantially different they are. So the sample size n, as n increases, so does the power of the significant test. This is because a larger sample size narrows the distribution of the test statistics. So factors affecting power, the four primary factors that affect the power of a statistical test are a level, difference between group means, variability among subjects, and sample size. Please take a look at these videos.
Of a statistical test to detect a relationship or difference. So this is how much of an ability do we have to actually find significance if it exists in the first place. So this comes down to what we kind of talked about with type 1 and type 2 errors, in that we make this decision based on a p-value, but were we right? Were we not right? Did we just not have enough power to find a difference when it exists in the population? We just couldn't find it. This is the probability of rejecting a null hypothesis when it is false, and therefore it should be rejected. So can we say that there is a difference, or can we say that there is a relationship based on our sample because it actually does exist in the population? Did we have enough power to find that in the first place? So Jacob Cohen, we'll talk about Cohen's d. He is the father of power analysis, and power is described as 1 minus beta. This is a different beta than regression, of course. Acceptable power is considered 0.8, but a lot of times 0.7 is really adequate, especially in education where we need a little bit more wiggle room, because there's so many other factors that go into just the environment of education. And if you have a power of 0.9, congratulations, that's excellent. Power analysis is usually done a priori, meaning before a study starts. You want to make sure that you have enough power to find significance before your study even starts. If you don't, then you're kind of wasting your time because you may not have a big enough sample, or you might be spending a lot of time and energy collecting this massive sample when you didn't need it in the first place. You could do it afterwards, but this can get really controversial. Some people really don't like this. To figure out what was your power after you've already done the study, it's kind of a waste of time. So here's another way of thinking about this. If the null hypothesis is true, meaning there is no difference in the population, then we want to fail to reject that because it's true, which means that we would have made a correct decision. Now, as a researcher, I could reject it, so I could interpret my p-value wrong, or I could do my calculations wrong, and I could reject it, and that would be a type 1 error. So these errors are really based on our decision, based on a sample of data. If the null hypothesis is actually false, meaning there is a difference in the population, we just couldn't find it, then that's an issue with power. And so all of this operates under the assumption that the null hypothesis is true. So if we can't find reason to reject it because we don't have enough power in the first place to be able to find a difference that exists, that's a problem. So power allows us to find a difference if it exists in the first place. And it's a measure of that. Power is a function of a lot of things. So it has to do with alpha. It's where we're 95% confident, 99% confident. We could be 90% confident, 80% confident, whatever you decide. Sample size, especially huge on sample size. The more people we include in the study, the more power we have. It is also based on effect size, which we'll talk about in just a minute. It is based on the type of stats test you're doing in the first place. So some tests need more power than other tests. And it also depends on the type of design that you are using. So let's talk a minute about what this idea of effect size is. So this blue and purple distribution, they are different. We can see that the means are different, and you'll notice that D, that's Cohen's D. What effect size is doing is it is measuring the strength of a phenomenon, the strength of that difference. So is the difference between these two, how strong is that? So what we're doing is we're trying to measure the size of the difference. And this comes down to the different hypotheses. So if the blue was the null hypothesis, and we are trying to see if the purple is significantly different than the blue, then we would fail to reject the blue if this difference isn't enough to be significant. If the purple is enough to be significant, then we would reject this hypothesis and we would in favor of the alternative hypothesis. So what we're really doing here is measuring the size, how far apart are these two groups. We've seen this when we did correlation and regression. We just didn't really talk about it in the same way. So with correlation, we're looking at the strength of that relationship. What is the size of the relationship? So is it weak? Is it moderate? Is it strong? Meaning, is it a small relationship? Is it a medium? Or is it a large relationship? Specifically, we talked about this with R squared. How much variance can I explain between the two? With regression, we talked about this with our betas. So the coefficients are actually our effect size. And I can't give you numbers on this because it's completely relative to your model and to the field that you are in. But you think about whatever coefficients went here, if beta 1 was a larger number than beta 2, then it has more influence on the overall equation when you actually do the math. So it would be a stronger effect than another one. We are going to talk in our practice and homework about Cohen's D, which is used in t-tests when we're looking at two different means and we want to see what is the effect, what is the difference between these two. It's a little bit more than just the difference between blue and purple. There's a little bit more that goes into it. So a small effect would be a 0.2, 0.5 is medium, 0.8 is large. I have had Cohen's D's of 1.4s that is quite large. When we get to ANOVA, we're going to talk about EDAs, which has its own system. So those are just kind of rules of thumb that we use to talk about effect size. So is it a large effect? Is it moderate effect? Is it medium? Is it large? So when it comes to these two groups, if this is the null and this is the alternative, this was a pre-post, let's say. So pre-test, everybody was here. Post-test, everybody was here. So we moved the entire distribution quite a bit because of whatever intervention we were doing. That is a large effect. And so the larger the effect size, the larger the power of the significance test, meaning we can shade in all of this stuff. It's quite large what we get to include in power. And that also means it's a smaller probability of making a type 2 error. And remember, this gets kind of confusing. We don't control the effect size. It just is what it is. And it's completely different depending on what your field is. We find this out a priori, meaning before the study, through the literature. So what are typical effect sizes in this field when looking at these variables? You could also do a pilot if you're not sure. So if the effect size is small to medium, then we have to have more subjects to find a significant result. Meaning it's really small, there is a significant difference, but it's small. So we need a lot of people to kind of fill in the gaps to show that there is a significant difference. Versus if the effect size is quite large, we don't need as many subjects because the difference is so big between those different distributions that we don't need as many subjects to kind of fill it in. Here's one way to look at this. So if we have an n of one person and one person, there is still a difference, but the power is only 0.26. So that's not adequate power to talk about this. So we don't have a lot that we can actually shade in. So even though these aren't changing, what is changing is the variance within each distribution. It's becoming tighter, it's becoming smaller, they're more peaked. And so this difference, even though that's not really changing, this is growing. And so we actually have more that we can shade in within each distribution. So here we have a power of 0.84. So more power as we get more people. And that grows very fast, as you can see. On the flip side, so more people, more power. On the flip side, larger effect, more power. So here we're changing the effect. So the distance between these two are very small. The distance between these two are quite large, or larger. And so again, when we think about power, we're able to fill in more of this difference. If we need to improve power, one way to do that is to relax your alpha. Meaning instead of being 99% confident, maybe we're 95%, or maybe we're 90%, or maybe we're 85%. You can use a parametric statistic, meaning a stronger statistic. Means tend to be good, but if you're using a proportion or something else, a total score, you might be able to do something different. You can increase the reliability of the measure. The more reliable a measure is, then the less variance there is between all of your scores. You can also use a one-tailed test. So when you think about drawing that distribution, we're putting all 5% error, if we're 95% confident, we're putting all 5% on one tail, on one side, instead of splitting that 5% on both sides. So we have a better chance of finding something if it's a one tail. It's a little bit risky though. Of course, increasing sample size is the absolute 100% easiest way to improve your power. And then you can also increase the sensitivity of the design or analysis, but that's sometimes really hard. We are going to look at tables where you can look up power and effect size and sample size and how all that's related. And there are computer programs to actually help you do this. So you can estimate your sample size in order to know that you have adequate power. You just need to know the effect size from a previous study, and you need to know what alpha level you have. So we're going to play with G-power. Let's do that now.
Okay, so this time I just want to show you a video about G-Power. G-Power is a free-to-use software used to calculate statistical power. The program offers the ability to calculate power for a wide variety of statistical tests, including t-test, f-test, and chi-square test, among others. Additionally, the user must determine which of the many contexts this test is being used, such as one-way ANOVA versus a multi-way ANOVA. In order to calculate power, the user must know 4 of the 5 variables, either number of groups, number of observations, effect size, significance level, or power. G power has a built-in tool for determining effect size. It cannot be estimated from prior literature or is not easily calculable.
A short demonstration of an a priori power calculation in G-Power, something missing from a lot of studies, but something that's actually a lot easier than you might imagine. So the first step is to download G-Power. So we're going to go to gpower.hhu.de. We'll then scroll down to download, and you can click to download G-Power in either Windows or Mac. Once that's downloaded and installed, we can then open up G-Power and take it from there. The first thing is to decide on the statistical test that we want to use. I find it's easiest to use the tests bar at the top. So under there, for correlations and regression, we've got various correlations and through to multiple regression, etc. If we want to compare means, we've got different varieties of t-tests, ANOVA, MANOVA, ANCOVA, etc. So to keep it simple, I'm going to start with an independent samples t-test. So we're comparing means of 2 independent groups. We've just got a small number of options that we can change. To start with, we're going to do a 2-tailed test. We then need to state the effect size that we want to be able to reliably detect. If we hover over it, we get the default effect size conventions of small, medium, and large. We can either use these, we can take an effect size from the literature, or ideally we can state what the smallest effect size is that would be considered clinically or practically meaningful, and then set our study up to be able to detect that. But for now, I'm going to take a medium effect size of 0.5. Our alpha level is 0.05 as usual. We then want to know how many participants would be required to be able to detect an effect size at least as large as the one we've stated, a certain percentage of the time. That percentage of the time is our power, and it's commonly set to 80%. So I'm going to set this to 0.8. And then all we're saying here is that we've got an even ratio of our 2 groups, so the same number of participants in each group. If I click calculate, we can see that detecting that effect size 80% of the time would require 64 participants in each group, so a total of 128 participants in our study. And that's it in a few simple steps. That is the a priori power calculation. We can explore it a little bit more. So we could see, for example, if we were only interested in detecting large effects, I can change that to 0.8, and our required sample size has dropped to 26 in each group and 52 in total. If we had a strong reason for performing a 1-tailed test that was justified and ideally pre-registered, then we can see that again it's reduced to 21 participants per group and 42 in total. We can also use this to explore different study designs prior to the study. So, for example, if it was possible to use the same group in both conditions and perform a paired samples t-test, we can see how many participants would be required for that. So under tests, means again, instead of 2 independent groups, this time we would have 2 dependent groups with matched pairs. Go for the same values that we had in the last calculation. And we're now down to a total sample size of 12 participants. So that's it for a brief demonstration of an a priori power calculation in G-Power. Hopefully you found that useful. If you've got any questions or anything else you'd like
Okay, again, G-Power is free. Open source program for power analysis and sample size calculation. Using G-Power, it's simple, clean interface, is easy to learn and easy to use. Great teaching tool. You can do a priori, post-hook, compromise, criterion, or sensitivity power analysis. It is widely used for doing power and sample size calculations for grants. So you can download the current version of G-Power from this website or link. No, you can also find help files, the manual, and the user guide on this website. So I think that's it. Thank you and good day.